Hi everyone, this is Anatol from SimScale speaking. I have with me right now Ashton from AWS and Richard, a colleague from SimScale. So today we are talking about some of our innovative features that we have on our platform, especially our LBM solver and its applications, and also a nice surprise later as well that we are introducing soon. Maybe you can just do a quick round of introductions. Maybe Neil, do you want to start?
Yeah, sure. So I'm Neil Ashton. So I'm a principal CFD specialist at AWS. I suppose my background has been, trying to develop a new CFD methods for, more than 10 years or something. Was an academic at Oxford University for a long time. And I came out to AWS basically to try and help the growing CFD community to take advantage of AWS, and SimScale is a great, kind of a company like that who is using AWS to help people to run CFD. So great to be here.
Great, thanks, Neil.
Hey, I'm Richard. I'm a product manager at SimScale. I joined the company 7 years ago when we just were about to start a platform and go online. I have a background in mathematics, but in recent years as product manager, I'm mainly responsible for our applications that are targeted with our new LBM solver for automotive aerodynamics, but also, for example, for urban wind scenarios, outdoor and also internal flows in buildings.
Great. And just a quick word about myself. So I'm one of the co-founders at SimScale, and right now also working in product management for a feature that we're going to discuss later towards the end of the podcast. Great. But for now, I'd sort of hand it over to Richard and Neil to talk about, about SimScale a bit, maybe, and what we are working on right now, and some interesting features and technology that we have in our backend right now.
Yeah, sure. Maybe for the folks that don't know SimScale yet, we might have a quick introduction what we do, so everyone is aware. So SimScale is a cloud-based simulation platform. We started 2012 and went online 2013. And meanwhile, we have more than 80 or 90 employees globally distributed with offices in Munich and also in the US, in Boston and New York. We have more than 250,000 users meanwhile. And over 1 million simulation projects have been computed on SimScale. And what makes us unique is basically that with SimScale, you can run high fidelity simulations directly in the browser or with the use of AWS cloud in the background for the heavy computations. So you don't have any requirements on your local hardware. So you can run simulations, for example, with the automotive aerodynamics cases that we discussed later that have several hundreds of millions of cells from a normal laptop, right? And you don't have to stop working on other projects. Meanwhile, you can continue your work. And this enables a lot more people to participate in the benefits that, for example, CFD and other computational methods have compared to not doing CFD or computations. And with SimScale, we have integrated all the different analysis types that we support, like fluid dynamics, incompressible, but also with heat transfer. We offer also structural mechanics, all in the same user interface. You can just open it in a browser, set up a simulation, and run it. We focused a lot on having a very user-friendly workflow that is easy to get started with, but yet it's still powerful, and you can do all kinds of very amazing simulations with the tool. And it just needs a very short startup time from beginner to actually being able to run high fidelity commercial grade simulations. Yeah, that's more or less what we do since the last 8 years. We have developed over time more and more features. We added new solvers to the platform, new physics that can be solved. and yeah, got a closer collaboration also with our partners as Amazon Web Services that we are using extensively. And with the recent addition that we had about 1.5 years ago, which is the Lattice-Boltzmann solver that we integrated together with Numeric Systems, which is the provider of the tool. We meanwhile also use the high performance graphics card instances that AWS provides. And with this, we can achieve a very high performance in the computational runs that we do.
And yeah, maybe we can talk a bit about the sort of applications, and maybe also where we see the sort of the big benefit for using CFD, for example, in automotive, right? And in which areas it can be useful, and how our solver comes into play, and how AWS actually helps us to sort of serve our customers there.
Neil, do you wanna from your perspective, as you have probably way more experience in automotive industry and aerodynamics, from your point of view, where the automotive industry is coming from with respect to aerodynamics, for example, and then we can maybe discuss where we are heading to.
Yeah, sure. I mean, the way I see it is, you're right. It comes from the end need, which is to design a better car, more efficient. And, obviously traditionally that was done kind of using wind tunnels and things like that, that gave you that ability to, take something in, change some part, chuck it on, turn on the wind tunnel, see if that made a difference or not. But often it was done more in a trial and error manner, because you couldn't really see what the flow field was doing. You were just measuring, force coefficients or something. And then, whilst there has been improvements in, wind tunnel technology in terms of diagnostics, PIV and things like that to understand, still, if you look at the major, companies or throughout the whole kind of chain of automotive, actually not that many of them use those diagnostics. They still tend to be, mainly kind of research-driven tools. So I suppose, the advantage of the CFD that, when I speak to engineers at the whole kind of range of automotive companies, it's the ability to see what's going on that really is the advantage. The second one, of course, is the speed and the cost of doing CFD. And I think we've definitely seen this evolution, I suppose, from, just having a workstation and saying, okay, I need to put more RAM on this, I need to get a faster CPU, and maybe I'll just have 2 workstations, but while it's running, I can't do anything else on it. I'm kind of locked out of my screen. I think we've all been there at some point in our career. And I think that's what's been really interesting, is then this kind of move to, a kind of more of a high performance computing sense. But then the challenge has been often, well, the experience of the end user is not to use a supercomputer, right? That's not their background. Their education has been in aerodynamics or CFD, not in computer science or Linux or, anything like that. So I think what is nice about the cloud and also what SimScale is doing is making it easier for people to kind of use those greater resources that, as you say, you can just be with a laptop. Like, people at AWS just have a laptop, right? I don't have a big workstation underneath me. And I also have a Mac, so most stuff doesn't work on a Mac of an engineering sense. So the ability to just spin something up in the cloud, I think, is having a real difference, and meaning that CFD can be more easily used. And now, ultimately, these companies who are using CFD to help design the cars or the parts of the future can do it faster, basically. So yeah, I think it has really been a game changer, and it's really great to see how SimScale are kind of enabling that, I suppose.
Yeah, I completely agree. I completely forgot the aspect even that it matters what software or what operating system you run on, right? So since 7 years, I'm running here on Linux, and I don't even know now that some tools only, for example, run on Windows, no Linux, no Mac. For us, it doesn't really matter, right? You just need a normal browser, and yeah, That's where the simulation runs, is just which operating system is most efficient for the tool, probably, right? And that brings a lot of flexibility.
And I think this is where this, you know, hopefully you're going to get onto it later, but there's also the fact that, you know, predicting what hardware you're going to need is something you don't need to really worry about, because you know how it is. Like some people would say, tell me what machine I should be buying, either a fat workstation or, you know, some high performance. And, you know, the costs are significant, the capital costs, the upfront costs. And you know, that's difficult, particularly, you know, especially if you're like a consultant or something, or a smaller company, and you're like, what do I invest in? So let's say you go down the CPU route. So you buy loads of CPUs, you do it. And then suddenly, you know, like you're going to show in a bit, that you've got this kind of LBM solver that could run on GPUs. And then they'd be like, oh, so should I have bought loads of GPUs instead? And then they're kind of locked into their software approach because of their hardware, which is completely the wrong way around, right? I mean, the hardware should enable the software. So if you can use, you know, AWS and just say, today I'm just going to be using, you know, a GPU, and tomorrow I'll be using a CPU, you don't have to make any upfront decision, do you? You just switch. So I think that's also where, if you're coming up with cool new methods that take advantage of another hardware, that's where the cloud, I think, comes in more than any other way, because you're not limited by, you know, having to chuck all these CPUs in the bin and go and buy loads of new GPUs. But maybe you'll get onto that in a little bit. Yeah,
totally agree. The variability of software, the evolution of the tools itself. Recently, with more and more tools switching over to GPU-based architectures, you can clearly see that the hardware is not anymore something that should be a decisive factor or limitation to you, right? And compared to what people were used to be doing in the wind tunnel, right? Now with CFD and getting basically more insights out of the analysis that you're doing compared to the wind tunnel. This enables also like more optimized solution that, for example, allow to find an optimum between drag reduction and still enabling sufficient cooling performance, maybe, right? If you talk about electric vehicles where cooling performance is also relevant, but even more the drag reduction is a major aspect of every new car design, right? Because that directly correlates with the range that you can achieve with the specific battery pack in that car, and range is, as we know, one of the main selling factors today in electric vehicle industry.
Yeah, and I think the key bit that I always remember when I was working in Formula One, or even after that, and with, you know, just some car companies, the question always used to come that, you know, we'd write some simulation or draw some design, let's say in CAD, and the always question was, but why is it better? You know, can you tell me why is that better? Because if you don't understand why, you're kind of just guessing almost. You just trial and error. Okay, I happened to move some part 50 millimeters to the right and it gave you a better answer, but why did it give you a better answer? And that's actually very difficult to get from a wind tunnel. It's in an industrial way, you know, because anybody who knows things about PIV or any of these, they're very time consuming. They make a mess of a wind tunnel. And a lot of the wind tunnel operators don't like it if you use PIV because they've got to go and clean it up afterwards. So actually, it's quite hard to know. Where, again, as you're saying, in the kind of the CFD, you can actually look into it and go, okay, now I see, because I moved this vortex moved this direction, or this changed the pressure here, which made this do. And so you can start to make really informed decisions rather than just directional. It just looked like it was better, you know? And I think that's why I always say to people, if you look at, you know, cars or planes or whatever, And Formula One is obviously the great example of this, the really highly curved three-dimensional surfaces. There's no way you would make that just by guessing. I mean, it's too complicated. You have to know that it's moving a vortex here or here. You know, you simply couldn't do that before. Okay, some of it's manufacturing. You know, some people say because manufacturing you can make curved surfaces easier, but I do think a lot of it is the CFD enabled to see actually what's going on.
Yeah, right. Yeah, and one aspect is now when we talk about aerodynamics and in vehicles, which is in a wind tunnel, I guess, easier when we talk about passenger vehicles. But if we go for like bigger stuff like heavy-duty trucks, for example, which is also important for them these days when the price of diesel, etc., increases, where efficiency is also a major effect here and a major concern. I guess it's also difficult in a wind tunnel to represent such larger structures accurately. What do you think?
Yeah, that's definitely the case. It's also more surface to manufacture, right? If you want to change something, it's also a bigger thing to change. I mean, I should say as well, just in case anyone watching or listening to this is an avid wind tunnel fan, we're not saying that you can't use wind tunnels, right? They have a place for verification, for sure, and I think that will be the case for many years to come. But you just can't get away from the fact that there is an inherent, you know, inflexibility of it, and particularly, fair enough, if you are a massive automotive OEM with your own wind tunnel, maybe 2 wind tunnels, fine, because you've already put the investment in, you already have the tunnel. But any company smaller than that is unlikely to have their own wind tunnel, so they're going to have to use somebody else's, and they're going to have to, you know, take stuff there. So there's also a kind of, you know, this democratizing simulation and aerodynamics, you know, that anyone can access to it. It's not just the big players who have the money to go, you know, into a wind tunnel and have all the manufacturing. So yeah, but of course accuracy is the key issue, and everyone knows, you know, if there's anything about CFD is it's easy for us to sit and say just use CFD, but if it's not accurate, then it's kind of pointless, really. So that's why moving to these kind of higher fidelity methods is actually part of what, you know, the whole CFD community needs to do to convince the wind tunnel community or convince others that CFD is actually accurate. You know?
Yeah, I'm not saying that wind tunnel is something that will not be there like in the future also alongside CFD. And I think a lot comes down to being able to couple these two tools more or less, right, closer together and get the benefits of both in whatever area each one has its benefit compared to the other. So I think we definitely don't say wind tunnel will be abandoned, but definitely there's advantages in using CFD for certain applications, or for just iterating faster, for having a tool to optimize easily your design and to get insights into very particular areas that you might not be able to currently with the wind tunnel methods.
Nice. And I mean, because Neil mentioned accuracy, right? I mean, obviously, this is also one of our concerns, right? I mean, having a cloud solution that is usable and, you know, very convenient for users which don't want to buy hardware and so on, it's great, right? But of course, you know, you have to make sure that it's accurate enough, right? Maybe we can go into that direction, right? Because we, of course, you know, we see this responsibility of ours that we want to make sure that, you know, things are accurate. And we do actually run validation studies. And yeah, maybe Richard can talk about one of the studies that we have done recently.
Sure. Yeah, that's a good point. So there's one famous automotive aero benchmark that was developed a couple of years ago together, I think, yeah, with Audi, BMW, and from the Technical University of Munich, where they basically built a realistic benchmark car. Because previously there were some benchmarks that were rather of academic nature, like the Ahmed body that probably everyone who did aerodynamics has seen in their lives, and that didn't quite represent the challenges with aerodynamics that modern cars face, and the details in the design that influence the results. So they came up with a very realistic car model, like could be a normal passenger car designed by Audi or BMW. And there has been extensive wind tunnel testing gone on this model. And also a lot of CFD companies have used it to benchmark their solution against the wind tunnel tests. And so did we. So we used 3 different versions of this car. It comes with a lot of different variations. So we tested the e-State-back, the fastback, and the notchback. And we used the same model scale that you would use in a wind tunnel test typically. I think it was a 60% model, and run it with our integrated Lattice-Boltzmann solver called Pacefish directly on the SimScale platform. And we used the latest at that time when we did the benchmark P3 generation instances that had the latest NVIDIA GPUs available. Now, as we talk, Neil knows that better than we do. There was a new generation of graphics instances released on Amazon with even more performance than the ones we used. But even with that instances, the P3 ones, we got very good performance of the solution. And also, of course, what matters is the accuracy of the results. So maybe quickly on the setup. The solution that we are using is a Lattice-Boltzmann method. So it's maybe a little bit different than traditional finite volume codes or finite element CFD codes that are derived from Navier-Stokes equations. They are basically derived from a mesoscopic point of view. So we're looking here rather at particles that travel through the fluid domain than a homogeneous fluid. And the advantage of this method is that it's particularly suitable for massive parallelization, and this makes it perfect application for graphical processing units. With the models we tested, we used typical cell sizes of about 160 million cells for the computational domain. And the simulation is run fully transient. So we run about 7 seconds of physical time at 16 meters per second, as is done in the wind tunnel. And the major point of comparison against wind tunnel tests were the drag coefficients in the cases that we did. So we compared the drag coefficients of the computational models with the ones from the wind tunnel tests. And we saw that in all 3 cases that we tested, the deviation was an average about 2.5, and in the maximum deviation still less than 5% for the drag coefficient of the car models we tested. So this shows that the method we used, and maybe Neil, you can also comment here on accuracy, what it means, and how important it is, and what maybe 2-3% deviation from wind tunnel actually mean. But we think these results are very, very encouraging, and show that with the methodology that we're using, and overall the computational time for these models, right, are within 8 hours. So this is all models that you can run overnight and you get the result the next morning. And you can also run them in parallel. 2-3% deviation from wind tunnel, we think is a good result for the state and the setup that we used. So we used also for the meshing, no very optimized setup. We used an automatic meshing that we have built. There's no manual adjustments to get maybe the peak performance that we could get, but this is a typical setup that we think our users would also do. Basically, get the car geometry on the platform, set the wind tunnel size, set the inlet speed, and hit go without any very detailed optimization of the setup.
Yeah, I think that's really good to hear, and it's really great that you're using this driver model, because you're right. The whole point of this model was that in the past you either used kind of two simple geometries, simple to make it relative, to make it important for kind of the automotive community, like you said, the Ahmed car body or some of these other bodies. Or the alternative was that you had to do it in collaboration with a car company who then wouldn't allow you to publish it because you were using their sensitive geometry. So the driver really helped to kind of open it up and allow people to use it. And as you rightly said, it's become a kind of de facto benchmarking model, really. And that's true not just for academics and software companies, but also for the car companies. They actually use these models to validate their wind tunnels, to validate their approaches. And it's a really good one. Now, it's not fully realistic. There are, of course, some things that are missing. And if you speak to, some car companies, they'll tell you that it doesn't accurately have this, and this, but it's still, I think, a good enough model to judge whether a method is promising or not. And I think, the fact that you've run your cases and got, that close in a unoptimized way, in a kind of more automated way, is very promising indeed. And I think also that the time is a really interesting one to capture, because, accuracy is should only be seen in relation to cost and time as well, because no reasonable person will want to have a simulation running for a week, because it's just not usable in a kind of industrial sense. So, and it is the GPUs that enable that, right? I mean, you're packing so much compute inside one of these. And it's true that we did just release the Amazon EC2 P4D instance that has the NVIDIA A100s. And, the benchmarks that we've seen so far is 2 or 3 times faster. So, it'd be interesting to see how you get on when you test those, because I'd expect you get an even bigger increase. And the important thing is, not only have we been seeing that they're 2 or 3 times faster, but if you look at the cost, it's not 2 or 3 times more expensive. So you typically actually see even more price performance. It's fantastic that you've been doing this. And what I would say as well, as a bit of a plug, I suppose, is that I organized this first automotive workshop that happened last year in December, I think it was. That was kind of more of a rushed affair that we did quite quickly, because I kind of wanted to get something done where we got everyone together to run this model. But we're actually going to be doing a second one in Berlin in August 2021. So I really hope you guys will kind of join in that, because it's kind of bringing the whole community together and trying to run these driver models.
Yeah,
so
for
that's
sure.
my plug over.
We would definitely love to join. Let's hope the Corona situation gets better until then, and we can actually meet in person. We actually we're just about to test these new A100 instances, and probably by the time this podcast becomes available, the results should be there, and maybe we can put it as some additional material next to it, so you can actually see how the performance and the cost performance increased for these new instances. It's also important for us, obviously, that we can provide our customers with the most cost-efficient solution that is available. And this is also the great benefit of working together with a cloud computing provider like AWS, that also we can just, with the click of a button, more or less, right, switch to new hardware, right, without any hassle or any investment on our side. So this is really something that helps us to be competitive also on the market, and to also compete with still widespread desktop software that is not able to adjust that quickly, because people usually don't want to always jump on the newest hardware, because that changes every 3 to 6 months with the new generation, and it's not feasible to always upgrade your local hardware that fast.
Yeah, so maybe, I mean, what would be interesting, because if there's people, I mean, you did a great job of introducing SimScale at the beginning, but from a practical point of view, how does it look, or how does it feel for someone who wants to run, let's say, a geometry using this? What's the sort of workflow, the way that they can collaborate on results, or how does that work?
Mm-hmm. Yeah, it's actually very convenient. So we allow our users to quickly log in on the platform, create a new project, and upload the geometry in all the major CAD formats that are available. So we support CATIA, Parasolid, SolidWorks files, or simply STL files, right? Which is the last resort geometry format that probably everyone can export to. This is all available on SimScale, so you can just simply upload your geometry as is. And this is one of the big factors that typically when you got very complex models or high fidelity models and prepare them for simulation, the first couple of days, maybe weeks, is spent in cleanup work for someone who just sits down and removes fillets or merges parts to make the geometry feasible for meshing. This is the first. So this is not necessary if you go with the Lattice-Boltzmann based solver on SimScale. So you upload your geometry as is and select one of the analysis types that allows you to run external aerodynamics. So we call this incompressible LBM. This allows an external aerodynamics analysis. So you select the analysis type, and then we populate basically your simulation tree already with predefined settings that are the most reasonable based on your car geometry that you upload and the use case that we have, which is external aerodynamics. And there's usually just a couple of settings that you need to adjust. Basically, you have to define your inlet speed. You can rotate the wind tunnel to maybe have some yaw angle inside, or adjust the floor of the wind tunnel to make up for the correct ride height. And that's about it. You can select the sizing or the resolution of your mesh or the computational grid, basically with qualitative means. So you can go from very coarse to very fine, and we then in the background select an automatic sizing of the cells for this particular setup. Or if you want to have more control, obviously what you can also do is define regions of refinements, define local cell sizes as you like them. So we basically offer the full flexibility with having local sizing, local refinements, region refinements, surface refinements, but also simply going with, okay, let's just do a course study at the beginning and see where we are, right? And that takes in total maybe 10 minutes maximum for the setup in this case. And as we're again working with the Lattice-Boltzmann method, the meshing step is basically an implicit step that works all the time. So the mesh is basically a background mesh where the geometry is used as collision surfaces basically that cut through the Cartesian grid. And with the Boltzmann method, with the Lattice-Boltzmann method, the fluid behavior is basically derived from that. And this makes the whole workflow very robust. So this is one thing, and obviously you click then on start to create the run. And what we then do is in the background, we package the setup, send it to AWS, fire up P3 or maybe P4 instance with the appropriate amount of GPUs that is needed to run this case based on the settings of the user. We do a first estimation step that gives us a very good approximation of the number of cells and the memory need that we have. And according to that, we set up the appropriate instance. The computation is fully run on AWS on one of the centers in Europe. And the user can just continue with their setup. So we can set up another study with slightly different geometry or different angles, different inlet velocity maybe, and run multiple studies at the same time. And your computer is fully free. You can do whatever you want besides the computation running on the cloud. And once the simulation is finished, you got an email notification with a link, or you can just simply log in back to the platform and post-process the results directly also in our online post-processor that is integrated in the platform. So you can get the forces out, you can get surface pressures, friction velocities, you can do nice animations of vorticity, all this kind of neat stuff that you want to share maybe with your team, or that also give you valuable insights on your performance, aerodynamic performance, right? So where you have the fluid detaching from the surface, these kind of results you have already included directly on the platform. And the fact that it's browser-based also enables us to collaborate with multiple stakeholders here. So if multiple designers are working on the same car, they can share the project within the team, and everyone can directly access the setup. They can review, they can peer review their setups. That's what we also often do internally here when we got a new project that with an application that maybe not everyone has done before. We just ask someone in the team that has the most experience, share the project with them. They can review it. We can give them edit access, so they can directly in place modify the project and run a new setup based on their recommendations. And that's very seamless. So there's no sending back and forth of actual files. There's no version 1, version 2, or version 1.5, 1.4, and so on. This is
final latest.
Yeah, exactly. No email sending of CAD geometries. That really makes it easy to collaborate with the team. And then in case when something doesn't go as smooth for the customer, there's also the option to have direct online support within the project. So we have an integrated chat solution where you can directly talk to a support engineer on our side. share the project, because the project is always private unless you explicitly share it. And then our support engineer can also take a look at the setup and provide some hints to where settings could be changed to improve the solution.
Nice. Yeah, I mean, that's exactly what I was saying right at the beginning, that there's a lot of users who really value that automation, I think, and really just want to focus on the end goal of, what's the better card design, for example. So they don't want to or need to really know what's in the middle. They just want to be able to focus on the CAD and then focus on the output. So that's kind of a nice way that you've got that set up, which seems very user-friendly and very kind of, customer obsessed, as we'd say at Amazon, that you just want to focus on what they need and take away the kind of heavy lifting of all the CFD setup. I think that's one of the things that, I think is unique to SimScale, I suppose, is that ease of use. We have, people who do maybe sometimes want to do it themselves, and, fine, if they do, they may have a good reason for it. But there's definitely a very large part of the community who, as I said, are aerodynamicists, let's say, and not CFD experts, and simply want to have a turnkey solution. And I think what you've done, and particularly with the LBM giving the kind of potentially increased accuracy and higher fidelity methods, is kind of really exciting to see.
Nice, yeah. And I mean, actually, I can jump in here again. I mean, this is actually a perfect transition to something I mentioned quickly before, right? So what we are right now doing is, or maybe to give you a bit of background, right? I mean, you've been doing this for a number of years, right? Over the years, you've built a sort of solid stack of, CAD processing software, meshing software, and simulation software, right? That is working well, right? Which has served our customers well using our Workbench, right? So this graphic interface that we serve via the web browser. And over the years, we've gotten requests again and again that certain companies, they have existing workflows, right? So they have an existing tool stack, an existing workflow where files go from the designer, maybe to the simulation analyst, through various stages. The sort of designers go to the simulation guys to actually run the simulation, get back results. There's sort of back and forth. It takes time. The analyst is sort of the bottleneck in actually running simulations and providing results and so on. So what many companies have asked us over the years is if there's any way that they can actually integrate SimScale into their existing workflows, right? So not basically giving the designs to the simulation expert that then goes to the Workbench and then simulates them and then goes back to the designer, even though, sharing the results and so on was already much more convenient than before. And this is actually what we are right now building, and probably it's going to be released by the time that this podcast is released. So we are actually opening up this sort of stack that we've built over the years by an API. We are launching this with some big partners, especially, and so there's different ways that you can use this, but in sort of the launch that we're doing is exactly kind of this thing that also Neil talked about, right? That enabling designers actually to run simulations, basically building a custom map for your company that allows designers to sort of just, throw in CAD files, maybe set 1 or 2 or 3 parameters, and then, for example, running an LBM, which, we don't have to do any CAD modifications. It's very robust. It will simply take whatever the designer throws at it and provide good results back, right? That the designer can then directly sort of digest and use.
That's really cool. I mean, I love that API-driven approach, and that's one of the things that people love about AWS is the kind of API, the ability just to kind of use that and build your own things. So that sounds like it could be a real game changer then, to allow people to kind of integrate it into their existing, and because we know that the CFD community, some don't have this, but there are companies, as you say, who kind of have an existing ecosphere of different tools, different approaches, and you often just need to fit inside it almost, so that sounds like a really, really nice approach. Okay, I'm looking forward to seeing it.
Yeah, this was actually a missing piece since long time, right? That people had to almost abandon workflows that they have built over the years, and then integration with SimScale was not as smooth as we hoped it would be, because obviously when you have a working system that might not be ideal, but it's harder to convince people to move to something else. And now we make this a very smooth transition to integrate SimScale in existing ecosystems, workflows, where you just basically replace a small piece of the whole stack with SimScale. And it also enables the customers to keep the workflow under control. Right? You have still the analyst that can build internally the application based on their experience, based on internal policies regarding quality criteria on sizing of meshes, for example, right? On optimizing these kind of things to get the best performance out of it. So they can keep this IP to their own and still enable all designers, for example, to participate in this new technology advancements and the new performance improvements and so on that come with the cloud and the new solver technologies.
Yeah, exactly. So yeah, great guys. I mean, I think we are about like 45 minutes in or so. Talked about many things. So yeah, I mean, again, we're excited to sort of work with AWS on this, right? Obviously, we use hardware, basically allowing our users to scale, and especially for the API, right? People could run a lot of jobs, and AWS allows us to serve that. So yeah, we are great to sort of partner there and work together. Great.
Yeah, another thing, maybe just to quickly touch on stuff that we initially mentioned, this where CFD provides a lot of benefits to other solutions is the optimization aspect, right? That you can do iterative changes and optimize the design towards specific design goals. That can also be served much better with an API solution, where you can integrate CFD with some kind of optimization technology that enables you to really get the best design that you can find for a specific set of constraints.
Yeah, exactly. So you can basically you can take a design, run a number of simulations at the same time again, of course, right? Where you might verify vary the geometry and all the simulation parameters, right? And get back results, and then automatically, based on that, decide if you want to modify your geometry in some way, and see if you can get a better result, and then iteratively improve your design automatically, and just run it overnight, right? It doesn't have to be on your computer or your workstation. You just run it on SimScale, AWS, and come back at some point, and you get your sort of optimized design. Good. Great. Then, was great talking to you, Neil. Thanks for taking the time. I think it's great that AWS has hired someone who has such a strong sort of background in actually CFD, right, and actually working in the industry and actually knowing really what they're talking about. So I think it's really great to have such partners. I think that's perfect, and we're happy to work with you all the time, of course.
Great. Thank you very much for inviting me on. It's great to speak to you both, and look forward to continued close collaboration and seeing these new things come out. So thank you very much.
Yeah. And hope to see you at the conference then next year.
Exactly. Yeah.
Right. Thanks, and see you soon.
Thanks.
Great. Thank you, guys.